In this video, I'll show you how to solve the ALEKS problem called identifying the electron added or removed to form an ion. To help you solve this problem, you are going to want to have access to a periodic table. We are going to be thinking about electron configurations with this problem, so I'm going to begin by marking up this periodic table to identify the areas that correspond to the S subshells, the P subshells, the D subshells, and then also down here, the F subshells, even though I don't think that we need the F subshells. And I want to remind you that when we're thinking about electron configuration, we like to place helium over here in the S area. Also want to remind you of the N values, the numbers that correspond to the different rows on the periodic table. And for the S and the P subshells, the numbers of the rows correspond directly to the N values. So that means that this portion of the periodic table, this portion of the periodic table corresponds to 2s. This portion of the periodic table corresponds to 4p. This portion down here corresponds to 7p. For the transition metals in the D block, they are one N value behind. So this row in the D block, even though it's in row number 4, it's actually corresponding to N equals 3. This is N equals 4, N equals 5, N equals 6. So that means that this row on the periodic table corresponds to the 5D electrons. And then the lanthanides and the actinides, they belong right here. They are one number even further behind. So this is 4F, and this would be the 5F. Okay, so, and if you're not familiar with this concept, that means that you probably are not super familiar with electron configuration. So I have a lot of videos on how to come up with electron configuration and how to use the periodic table in this way. So just kind of go back and look for some of those videos to get you brushed up. So this question, or this problem, has got two different questions to it. It's got three different elements, and it's asking us to identify where electrons would be removed or where electrons would be added if these elements were to ionize. And I want to start with this part of the problem first because this part of the problem is easier. So this is asking us which subshell, meaning like 3s or 4p, which subshell would the electron be added to if these different atoms were to form a -1 ion? Okay, so to help us solve this part of the problem, we're going to take that atom, we're going to locate the atom on the periodic table. Potassium is our first element right there. That's where it's located. So the subshell to which an electron is going to be added to form a -1 ion, that means if we're going to plop one more electron into this atom, where is it going to go? We can get that by reading the electron configuration up to the element, up to potassium. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And if we were to add one more electron, it's going to go just into the next spot over. For potassium, it would be electron number 20. That makes it just like calcium in terms of its electron configuration. If we added one more electron to potassium, that electron would be this guy right there, which is in the 4s subshell. That's its location. That's all. That's kind of all we have to do. If we're answering this part of the ALEKS problem, this subshell to which the electron is added, this is going to just be the next electron, or the location or the subshell of the next electron to be added if you just kept going, if you keep going with the electron configuration. So the next element that I have on my problem is zinc. Zinc is located right here. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And if we were to add one more electron to make it a -1 anion, that next electron would be located right here, right there, which is 4p. And the last element that I have on here is neon. Neon is right there. 1s2, 2s2, 2p6. If I added one more electron, it would go into, we're just going to keep going with the electron configuration. If we were going to keep going from neon, the next spot would be in the 3s. It would be 3s1. So our next subshell is 3s. And I feel like that's not too bad. Just where's the location of the next electron if you keep going. Now this part that I skipped over with, this one is a little bit trickier. It's not quite as straightforward as this. The subshell from which an electron removed is going to be the highest N value n value subshell. Highest occupied, or highest, oh, we'll just leave it at that, the highest n value subshell. Okay, so for potassium, again, we want to go back to the location of potassium on the periodic table, and this time we really need to think a lot about potassium's electron configuration, and maybe even write it down. We have 1s2, maybe I'll write it down, 1s2, and then we have 2s2, and also 2p6, and then we have 3s2, 3p6, 3s2, 3p6, and then we have 4s2 right there. Now, if we remove one of these electrons to form the +1 ion, it's going to come out of the highest n value. For potassium, oh wait, I wrote that wrong, it's 4s1. For potassium, the highest n value is 4, and the highest subshell in n equals 4 is 2. So that for potassium, so that is going to come out of the 4s. Coincidentally, it is also the last electron that we added in the electron configuration, but that is just a coincidence. Let's just keep going. Actually, I'm going to skip down to neon. We'll do neon next. Okay, so for this, again, we're looking for the highest n value subshell. So electron configuration for neon is going to be 1s2, 2s2, 2p6. 1s2, 2s2, 2p6. The highest n value is n equals 2, and we are looking for, of these, the highest n value, we're looking for the highest energy subshell, which is the last one that we added electrons to, the 2p subshell. So maybe we'll add a little note to this. The highest energy in the highest energy orbital or shell, subshell, in the highest n value. We'll go with that. The highest energy orbital in the highest n value. So highest n value was n equals 2. Highest energy orbital was the p, 2p6. All right, here's our last one. We have zinc. And zinc is located right here. Let's write its electron configuration. It's going to be 1s2, 2s2, 2p6, 1s2, 2s2, 2p6, 3s2, 3p6, 3s2, 3p6, got us to here. 4s2, 3d10, 4s2, 3d10. The electron that we're going to remove is going to be in the highest n value, which is n equals 4. The highest n value, so it's not necessarily the last electron that we added, it's an electron in the highest n value. For zinc, that's going to be 4s. Now, so this is going to be tricky, especially when you're dealing with the elements that are in the transition metal area or the D block area. For example, if you had cobalt, the electron configuration of cobalt would end in 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. The last electron that you remove would not be this 3d electron. It would be the electron in the highest n value, which is the electron in this 4s orbital. This is a tricky concept. I know if you take your time and work on it, especially if you write the electron configuration out, then you're definitely going to be good to go on this problem, but just take your time working on it.